welcome to this problem walkthrough. In this session, we'll dive into LeetCode problem number 834, titled Sum of Distances in Tree. This problem requires us to calculate the sum of distances between all pairs of nodes in an undirected tree, and we'll explore an efficient approach to solve it. Let's get started. In this problem, we are tasked with processing an undirected tree, which consists of n nodes labeled from 0 to n1. The tree is represented by a list of edges, where each edge connects two nodes, and there are exactly n1 edges since a tree is minimally connected. What we need to calculate is an array, answer, where each element answer, I, represents the sum of distances from node I to all other nodes in the tree. For example, if we focus on a specific node, say node I, we calculate the distance to every other node in the tree and add them together to get answer, I. The input includes the number of nodes, n, which can range from 2 to 30,000, and the list of edges that define the tree's structure. The output is this distance sum array, with one entry for each node in the tree. To better understand this problem, let's consider an example where n equals 6 and the edges are defined as 0, 1, 0, 2, 2, 3, 2, 4, 2, 5. When visualized, the tree has node 0 at the root, with nodes 1 and 2 directly connected to it. Node 2 further connects to nodes 3, 4, and 5. Now, for node 0, we calculate the sum of distances to all other nodes. The distance to 1 is 1, the distance to 2 is 1, and to nodes 3, 4, and 5, the distances are 2 each. Summing these values, we get 8 as the result for answer, 0. Similarly, for node 1, the distances to 0, 2, 3, 4, and 5 are summed up, giving us 12 as the result for answer, 1. This process continues for each node in the tree. Focusing now on node 2, the distances to other nodes in the tree are as follows. Distance to 0 is 1, to 1 is 2, and to 3, 4, and 5, the distances are all 1. Adding these up, the sum of distances for node 2 is 6. Similarly, for nodes 3, 4, and 5, which are leaf nodes, their distance sum is 10 each. This is because their only connection to the rest of the tree is through node 2. From here, calculating the distances to nodes 0, 1, and the other leaves results in the same total for each of these nodes. Let's explore another example where the tree is smaller. If n equals 1 and there are no edges, the tree consists of a single node. Since there are no other nodes to calculate distances to, the sum of distances for this node is simply 0. Now, consider a slightly larger tree where n equals 2 and the edges are 1, 0. This forms a simple line between nodes 0 and 1. For node 0, the only distance is to node 1, which is 1. Similarly, for node 1, the only distance is back to node 0, which is also 1. Therefore, the output array in this case is 1, 1. Finally, let's consider the constraints and edge cases that we need to account for. First, when n equals 1, the tree has a single node, and the distance sum is 0 because there are no other nodes. For a minimal tree with n equals 2, both nodes have the same distance sum since there's only one edge connecting them. When n is very large, approaching the upper limit of 30,000, the algorithm must be designed to handle these computations efficiently without running into performance issues. We should also consider unbalanced trees, where one branch is significantly deeper than others, and dense subtrees, where many nodes are closely clustered together. These edge cases ensure that our solution is robust and performs well under various scenarios. To solve the problem, sum of distances in tree, we need to calculate the total distances from each node to every other node in an undirected tree. Let's start by considering a few approaches. First, the brute force approach involves performing a BFS or DFS for each node. The idea here is to compute the sum of distances by traversing the tree starting from every single node. While the implementation is straightforward, the major drawback is its inefficiency. Since traversing the tree for one node takes n time, and we repeat this process for all n nodes, the total time complexity becomes n squared. This is computationally expensive and impractical for large trees with thousands of nodes, as it leads to a lot of redundant calculations. To address this inefficiency, we turn to an optimized approach using two-pass DFS. Here, we aim to reduce redundant calculations by reusing overlapping computations. The key idea is to first compute the total distances for one node, then propagate these results to other nodes by leveraging the relationship between parent and child nodes. Specifically, when transitioning from a parent to a child, we observe that distances to nodes in the child's subtree decrease, while distances to nodes outside this subtree increase. Using this insight, we can develop a more efficient solution. Now, let's break down the two-pass DFS approach step by step. In the first DFS, we start from node 0 and calculate two things: the size of each subtree, represented by the subtree_count array, and the sum of distances for node 0, stored in res. 0. Once this is done, we perform a second DFS to propagate results from node 0 to all other nodes. The key formula here is res v equals res u plus n 2 subtree_count v, which allows us to calculate the distances for a child node v using the result of its parent node u. This formula works because moving from the parent to the child shifts distances to nodes in the child's subtree and those outside it in a predictable way. The beauty of this approach is that both DFS traversals run in O(n) time, resulting in an overall time complexity of O(n), which is highly efficient. We also considered an alternative approach using BFS, which operates on a similar idea. However, BFS is less intuitive for propagating distance calculations and tends to make the implementation more cumbersome. For these reasons, we decided to stick with the two-pass DFS approach. When choosing our strategy, we carefully weighed the trade-offs. Compared to the brute force approach, the two-pass DFS method requires additional memory to store the subtree_count and res arrays. However, this is a small price to pay for the significant performance improvement. While BFS could also be used, DFS aligns more naturally with recursive tree computations, making it simpler and more elegant to implement. The most critical insight that makes this approach so effective is the formula res v equals res u plus n 2 subtree_count v. This formula is the cornerstone of our solution, as it allows us to efficiently calculate results for child nodes by building on the parent's result, avoiding redundant work. Overall, the two-pass DFS strategy strikes an excellent balance between clarity, efficiency, and scalability, making it the ideal choice for solving this problem, even for large inputs. In LeetCode problem number 834, we are tasked with finding the sum of distances between all pairs of nodes in an undirected tree. Trees, unlike general graphs, are acyclic and connected, which allows us to leverage certain traversal techniques like depth-first search, or DFS. With up to 10,000 nodes, we need an efficient approach to handle this problem within linear time. The solution involves a two-pass DFS strategy. In the first pass, we perform a bottom-up traversal, starting from an arbitrary root node, such as node 0. The goal is to compute two key pieces of information for each node: the size of its subtree and the sum of distances to all nodes within that subtree. As we recurse through the tree, we calculate the size of a node's subtree as 1 plus the sum of subtree sizes of its children. Similarly, the distance sum for a node, denoted as dp, u, is the sum of the distances from that node to all other nodes in its subtree. This is computed by adding the distances from its children, adjusted for their respective subtree sizes. By the end of this pass, we have important intermediate results stored for each node, which we'll use in the next step. In the second pass, we switch to a top-down DFS traversal. The goal here is to compute the final distance sum for every node using the results obtained at the root in the first pass. Starting from the root node, we propagate the results to its children based on a key relationship. For any child node v of a parent node u, the result for v can be derived as res v equals res u subtree_size v plus n subtree_size v. This equation works because we subtract the contribution of nodes in V's subtree while adding the contribution of all other nodes outside of it. As we propagate this calculation to each child recursively, we efficiently compute the result for all nodes without redundant recalculations. This process leverages the tree structure and the fact that trees have no cycles, ensuring that we can traverse and compute results efficiently. The combination of bottom-up aggregation and top-down propagation allows us to compute the solution in linear time. Additionally, the reuse of previously computed values ensures that our approach is highly optimized. The formula used in the top-down pass not only avoids redundant computations but also ensures our solution's linear complexity. To implement this algorithm, we use a few essential data structures. First, we represent the tree as an adjacency list, which is both memory efficient and well suited for quick traversal. Then we maintain three helper arrays. The subtree_size array tracks the size of each node's subtree, dp stores the sum of distances from a node to all nodes within its subtree, and res holds the final result for each node. In terms of complexity, the time complexity of this approach is O(n), because each DFS pass traverses all nodes exactly once. The space complexity is also O(n), primarily due to the adjacency list and helper arrays. This efficiency makes the algorithm scalable to large trees. To begin implementing, we first construct the adjacency list representation of the tree. Then, we initialize the helper arrays, setting all values to 0, to prepare for the DFS calculations. The implementation proceeds with the two DFS passes. In the first DFS, we traverse the tree in a bottom-up manner to compute the subtree size and dp values for each node. Starting from the root node, we recursively visit its neighbors, skipping the parent node to avoid backtracking. For each node, we update its subtree size by summing the sizes of its children and incrementing by 1 for the node itself. Similarly, we calculate the dp value for the node by summing the dp values of its children and adding their respective subtree sizes. Once the first DFS completes, we move to the second DFS pass. Here, we calculate the final results using the relationship derived earlier. Starting with the root, we propagate calculated values to its children. For each child, we adjust the dp value based on the subtree sizes, ensuring that we account for nodes both inside and outside the child's subtree. This recursive process continues until results for all nodes are computed. The final array res is then returned, containing the sum of distances for each node. To understand the algorithm better, let's walk through an example with 6 nodes and edges connecting them as shown. During the first DFS, we calculate the subtree size and dp values. For instance, node 2, which is connected to nodes 3, 4, and 5, has a subtree size of 4, as it includes itself and its 3 children. The dp2 value is computed as the sum of distances from node 2 to nodes 3, 4, and 5, adjusted by their subtree contributions. Once the first pass is complete, we proceed to the second DFS. Starting from the root node, we use the derived relationship to compute results for all other nodes. For example, the result for node 2 is calculated by excluding the contribution of its subtree from the root's result and adding contributions from nodes outside its subtree. This step-by-step computation ensures that the final results are accurate and obtained efficiently. By the end, we have the res array fully populated, containing the sum of distances for all nodes. The final results for the given example are stored in the array res equals 8, 12, 6, 10, 10, 10. This output represents the sum of distances from each node to every other node in the tree. For instance, node 0 has a total distance of 8 to all other nodes, while node 1 has a total distance of 12. To ensure the correctness of our solution, we must also consider edge cases. For a single node tree, where n equals 1, the result is simply 0, as there are no other nodes to calculate distances to. For a line-shaped tree, the algorithm should correctly propagate distances along the chain, ensuring accurate results. Finally, for a large balanced tree, the linear time complexity ensures that the solution remains efficient even as the input size grows. This combination of correctness, efficiency, and scalability makes our approach robust for solving the problem of summing distances in a tree. Here, we start by importing the necessary module, defaultIct, which will help us efficiently create our adjacency list representation of the tree. The core function, sum of distances in tree, begins by accepting the number of nodes, n, and the list of edges that define the tree structure. Using a loop, we build the tree as an adjacency list, where each node maps to a list of its neighbors. This makes traversing the tree much easier. Next, we initialize 2 arrays, res, which will store the result for each node, and count, where each entry starts at 1 and will represent the size of the subtree rooted at each node. Now, we define the post_order function. This function is a depth-first search, DFS, that calculates the size of each subtree and the initial distance values. It recursively visits child nodes, skipping the parent to avoid revisiting the same edge. As it traverses back up the tree, it updates the count array to reflect the size of the subtree and adds the cumulative distances from children to the current nodes result in the res array. This step sets the foundation for the next traversal, where we will propagate these results to all other nodes. After the post-order traversal, we move to the pre_order function, which performs a second DFS. This time, the goal is to propagate the distance calculations to all nodes in the tree. For each neighbor of the current node, the formula res neighbor equals res node count neighbor plus n count neighbor allows us to compute the result for the child node based on the parent's result. This adjustment accounts for the distances gained or lost when shifting the route from the parent to the child. Finally, we perform the two DFS traversals, starting from the root node, which is assumed to be node 0, with an initial parent value of -1 to indicate no parent. The post_order traversal calculates the subtree sizes and initial distances, while the pre_order traversal adjusts these distances for all nodes. Once both traversals are complete, the res array holds the sum of distances for every node in the tree, and we return it as the final result. Here, we start by defining the Java implementation of the solution. The method SumOfDistances takes the number of nodes, n, and an array of edges as input. First, we construct the tree as an adjacency list. This representation helps us access the neighbors of any node efficiently. We initialize an empty list for each node, and then, for each edge in the input, we add the corresponding connections to the adjacency list. Next, we declare two arrays, res to store the final results for each node and count to track the size of the subtree rooted at each node. We also prefill the count array with ones because each node initially contributes a count of 1 for itself. From here, we perform a post-order depth-first search to calculate the size of the subtrees and the initial distance sums for the root node. Once the post-order traversal is complete, we perform a pre-order DFS to propagate the calculated distances to all other nodes in the tree. Finally, we return the res array, which contains the sum of distances for every node. The post-order method is where we compute the size of the subtree for each node and the initial distances starting from the root. For each neighbor of the current node, if it is not the parent, we recursively call post-order on that neighbor. After returning from the recursive call, we update the subtree size of the current node by adding the subtree size of the neighbor, and we update the initial distance sum by adding the distance sum of the neighbor plus its subtree size. This ensures that each node's subtree size and distance are calculated correctly. Next, the pre-order method is used to propagate these results to the rest of the nodes. For each neighbor, we calculate its result based on the current node's result, subtracting the neighbor's subtree size and distance contribution, and adding the contribution from the rest of the tree. This ensures all nodes are accounted for. We then recursively call pre-order for the neighbor to continue propagating the results through the tree. This dual DFS approach ensures accurate results while maintaining efficiency. We begin by examining a small tree example with 4 nodes and edges connecting them as described. The first step is to construct the tree's adjacency list. Using the edges provided, the tree is represented as a dictionary where each key is a node, and its value is a list of connected nodes. This adjacency list will help us traverse the tree efficiently. Next, we perform a post-order depth-first search starting from node 0, which we treat as the root. During this traversal, we visit child nodes to calculate 2 key pieces of information: the size of each subtree rooted at a given node, and the sum of distances from that node to all others within its subtree. For example, when visiting node 1, we find it has no further children, so its subtree size is simply 1, and the sum of distances within its subtree is 0. These results are stored in the arrays count and res respectively, which will update as we process more nodes. Back at node 0, we incorporate the results from node 1 by adding its subtree size and distance sum to those of node 0. We then proceed to node 2, another child of node 0, and explore its subtree. Visiting node 3, which is a child of node 2, we find it has no further children, so its subtree size is 1, and its distance sum is 0. Returning to node 2, we update its results by including those of node 3. Node 2's subtree size becomes 2, and its distance sum is 1, accounting for the edge between nodes 2 and 3. Finally, back at node 0, we combine the results from both of its children, nodes 1 and 2. The total subtree size at node 0 is now 4, and the sum of distances from node 0 to all other nodes is 3. With these post-order results calculated, we proceed to the pre-order DFS to propagate distance sums. Starting again from node 0, we calculate the distances for its children. For node 1, the result is updated using the formula: subtract the size of node 1's subtree and add the size of the remaining tree. This gives us a result of 5 for node 1. Similarly, for node 2, the result is adjusted to 3, and its child, node 3, is updated to 5. The final distances for all nodes are 3, 5, 3, 5. Now, let's consider a balanced tree with 6 nodes. Using the provided edges, we construct the adjacency list, creating a tree structure where node 0 connects to nodes 1 and 2, node 1 connects to nodes 3 and 4, and node 2 connects to node 5. With the tree constructed, we perform a post-order DFS starting from node 0 to compute subtree sizes and initial distance sums. Visiting node 1, we further explore its children, nodes 3 and 4. Since both nodes 3 and 4 have no children, their subtree sizes are 1, and their initial distance sums are 0. These results are added to those of node 1, updating its subtree size and distance sum to reflect its entire subtree. Returning to node 1, we combine the results from nodes 3 and 4. Node 1's subtree size becomes 3, which includes itself and its 2 children, and its distance sum is updated to account for the distances between these nodes. Next, we move to node 2 and explore its only child, node 5. Since node 5 has no children, its subtree size is 1, and its distance sum is 0. These values are added to node 2, giving it a subtree size of 2 and a distance sum of 1. Finally, back at node 0, we combine the results from its 2 children, nodes 1 and 2. Node 0's total subtree size is now 6, and its distance sum is 8. With the post-order results computed, we proceed to the pre-order DFS to update the distance sums for all nodes. Starting at node 0, we propagate the results to its children and further down the tree. The final distance sums for all nodes are 8, 8, 8, 12, 12, 12, indicating the total distances from each node to all others in the tree. Finally, let's analyze a line graph with 3 nodes connected sequentially. The adjacency list for this tree is straightforward, as each node is connected to its immediate neighbors. Starting with a post-order DFS from node 0, we visit node 1, which leads us to node 2. Since node 2 is a leaf node, its subtree size is 1, and its distance sum is 0. Returning to node 1, we update its results to include those of node 2. Node 1's subtree size becomes 2, and its distance sum is 1, reflecting the edge between nodes 1 and 2. Back at node 0, we incorporate the results from node 1, giving node 0 a subtree size of 3 and a total distance sum of 3. Next, during the pre-order DFS, we propagate the results. Node 1's result is updated to 2, and node 2's result becomes 3. The final distances for all nodes are 3, 2, 3, representing the sum of distances from each node to every other node in the graph. In this problem, the time complexity of the solution is primarily determined by the operations performed during 3 main phases: tree construction, post-order depth-first search, and pre-order depth-first search. First, constructing the adjacency list involves iterating through the input edges. Since the tree has n nodes and n1 edges, this step takes n time. Next, during the post-order DFS, each node is visited exactly once, and its neighbors are processed. For every node, the algorithm calculates 2 important values: the size of its subtree, stored in the count array, and the sum of distances within its subtree, stored in the res array. Since each edge in the tree is traversed twice, once from each endpoint, the total work done here is also n. Now, let's consider the pre-order DFS. Similar to the post-order traversal, each node is visited exactly once, and its neighbors are processed. The key operation here is propagating the result from the parent node to its children, which can be done in constant time for each neighbor. This efficient propagation ensures that the total work done during the pre-order traversal is also n. When we combine the time complexities of tree construction, post-order DFS, and pre-order DFS, we get n for each phase. Adding these together gives us an overall time complexity of n for the entire solution. Next, let's analyze the space complexity. The adjacency list representation of the tree uses a dictionary where each node is mapped to a list of its neighbors. Since there are n nodes and n1 edges, the space required for this representation is n. Additionally, both the post-order and pre-order DFS utilize recursion, which means there is space usage for the recursion stack. The depth of the recursion stack depends on the height of the tree. In the worst-case scenario, where the tree is skewed, the height is n, leading to n stack space. In the best-case scenario, where the tree is balanced, the height is log n. Finally, the solution uses two auxiliary arrays, res for storing the results and count for storing subtree sizes, each of which requires O(n) space. Adding all these components together, the total space complexity is O(n) for the adjacency list, O(n) for the recursion stack in the worst case, and O(n) for the auxiliary arrays. This gives us a total space complexity of O(n). In the best case, where the tree is balanced, the recursion stack usage reduces to O log n, but the overall complexity remains O(n), since the space for the adjacency list and auxiliary arrays dominates. Comparing this to a naive approach, where we would calculate the sum of distances for each node independently using a BFS or DFS, the naive method would require O(n) time for each traversal, resulting in a total time complexity of O(n squared). Space complexity for the naive approach remains O(n) for the q-in-visited array. However, our optimized approach avoids redundant calculations, reducing time complexity to O(n), while maintaining efficient O(n) space usage. Finally, let's validate the time complexity mathematically. For a tree with n nodes and n1 edges, constructing the adjacency list takes O(n). During the postorder and preorder DFS traversals, each node and edge are processed exactly once, leading to O(n) for each traversal. Summing these components confirms that the overall time complexity is O(n), which is optimal for this problem. In conclusion, this optimized solution significantly improves upon the naive approach by reducing the time complexity from O(n squared to O(n), while keeping the space complexity at O(n), making it both time efficient and space efficient. When solving the sum of distances in tree problem, there are a few common mistakes to watch out for. One major issue is relying on a brute force approach, where you compute the sum of distances for each node individually. This involves performing a depth-first search for every node, resulting in a time complexity of O(n squared). For large trees, this becomes infeasible. Instead, you should use dynamic programming and the properties of trees to reuse computations, which can bring the complexity down to O(n). Another mistake is representing the tree as just a list of edges without converting it into an adjacency list. This can lead to inefficiencies during traversal, so always pre-process the edges into an adjacency list for efficient DFS or BFS operations. Lastly, mishandling edge cases is a frequent pitfall. Examples include overlooking single-node trees, disconnected graphs, or two-node trees. Each of these scenarios needs to be explicitly tested and handled in your code to ensure correctness. Another frequent mistake is overcomplicating the management of parent-child relationships during traversal. Some solutions manually track these relationships, which can lead to redundant code and unintended bugs. A better approach is to use the recursion stack or the adjacency list structure to handle these relationships implicitly. Additionally, issues often arise when implementing the postorder and preorder DFS strategy, particularly with the propagation of results. If you fail to update results properly while transitioning between nodes, your answers will be incorrect. To avoid this, it's crucial to ensure that the results are propagated correctly by combining the parent's result with the contributions from the subtrees. Getting these two aspects right, managing relationships and propagating results, will make your solution more robust and accurate. The sum of distances in tree problem often appears in interviews because it tests your ability to optimize computations using tree properties. The key insight here is that the problem can be split into two parts: first, calculating the initial distance sum for a root node, and second, propagating the results to other nodes. This is typically achieved using a combination of postorder and preorder traversals. Recognizing this pattern is essential, as it represents a classic example of using dynamic programming on trees. Similar techniques can be applied to other problems involving subtree calculations. Interviewers generally expect you to optimize the naive O(n squared approach to O(n) by reusing subtree information efficiently. During interviews, it's important to clearly explain your thought process, particularly how you calculate the initial distance sum and propagate results. Using diagrams to illustrate these steps can greatly enhance your explanation and demonstrate your understanding. To strengthen your understanding of tree traversal and dynamic programming, it's helpful to look at related problems. For instance, LeetCode 3.10, minimum height trees, uses similar traversal and optimization techniques to minimize the height of trees. LeetCode 1.24, binary tree maximum path sum, involves dynamic programming on trees to compute maximum sums, which is another common pattern. LeetCode 543, diameter of binary tree, focuses on calculating distances in a tree using post-order traversal, a technique directly relevant to the problem at hand. Finally, LeetCode 987, vertical order traversal of a binary tree, introduces additional constraints like maintaining vertical order during traversal, which can help you practice multi-dimensional tree traversal. These problems all build upon the fundamental concepts of subtree calculations and dynamic programming, so working through them can significantly boost your intuition and problem-solving skills. There are several approaches to solving this problem, each with its own trade-offs. The naive brute force method has a time complexity of O(n) squared, and involves performing a depth-first search for every node to calculate distances. While simple to implement, it becomes impractical for larger inputs. The optimal approach combines dynamic programming with DFS, using post-order traversal to compute subtree sizes and distance sums, and then pre-order traversal to propagate results efficiently. This reduces the time complexity to O(n), but it requires careful implementation of both traversals. An alternative approach is centroid decomposition, which involves decomposing the tree into smaller components for recursive computations. While this technique is more complex and overkill for this specific problem, it's useful for other advanced tree problems. The key takeaways are to avoid brute force methods by leveraging tree properties in dynamic programming, ensure your tree traversal logic is robust, and practice related problems to build a strong intuition for subtree-based optimizations. Great job! To wrap up, we reviewed the key insights and solution strategies for solving this problem. We discussed how tree traversal and dynamic programming were used to solve the problem efficiently, and we summarized the time and space complexities. Remember to practice similar problems to strengthen your understanding. Thank you for watching, and keep up the great work. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!